Okay, in the very first example, we're working with optimization, which means maximizing or minimizing a function depending on what you want. For example, profit needs to be maximums, cost needs to be minimums, but then it can also have physical applications as well. So in this case, we're looking at an actual graph. You have the square root of x minus 8. So this moved to the right 8 units. I counted by 2s. And it looks like your ballet arm. And so you're asked to find the shortest distance between the point 2, 0 and the function square root of x minus 8. So in that case, what you're looking for is the shortest distance. But I'm going to give you a heads up. The calculus portion of this doesn't work, and let me show you why. The first reason is because of the domain. So the domain for this function has to remain positive inside that radical. And so that has to be x greater than or equal to 8. And you'll notice what they asked you, the point is outside of your domain. So it doesn't really have a relationship with your function. This is problem number 12 in the book. So don't feel like I'm pulling this out of left field. It's just something that you may run into. And so I want you to be prepared to be able to answer something as a mathematician would. So if we look at this and we say, okay, we're going to go ahead and say, I want the closest distance, so I need the distance formula. So the square root of x sub 2 minus x sub 1, quantity squared, plus y sub 2 minus y sub 1, quantity squared. And I look at the points that I have. My 2, 0 is my x1, y1. And then you say, okay, I need another point, x2, y2. And so I look at my function. My function uses x's, and my y values come from the square root x minus 8. And so if I plug that into my distance formula, and so I have the square root of x minus 2 squared plus the square root of x minus 8 minus 0 squared. The 0 goes away. X minus 2 squared, if we FOIL it, we know x times x, x squared, negative 2 times x, and then negative 2 times x, that's negative 4x, and negative 2 times negative 2, positive 4, plus the square root of x minus 8 quantity squared makes the radical disappear. And so I get x minus 8. Simplifying that, I have x squared minus 3x minus 4 by combining like terms. So when I derive it, the derivative of the distance is the chain rule, because that radical can be rewritten as a half. So the 1/2 drops, the inside stays the same. Subtract 1 from the exponent. And then the inside 2x minus 3 is the derivative of the inside. So cleaning it up, I have 2x minus 3 in my numerator and 2 times the square root of x squared minus 3x minus 4. Now remember, in my original domain, I wanted everything greater than or equal to 0. So when I look at the two things that cause my derivative to equal 0 or go undefined, my zeros come from 2x minus 3, which gives me x equals 3/2, not in the domain. And then my undefined points come from when the denominator equals 0. This one is factorable. What multiplies to negative 4 adds to negative 3 would be negative 4 and positive 1. So x minus 4, x plus 1. Now if if it wasn't factorable, I would check with my quadratic formula and see if I had any values in there. But because this has to be always positive, even if I do get critical numbers, they're not going to change the sign of the derivative. And so if you notice, all of the critical numbers I have, -1, +3/2, and +4, not in my domain. And so in this case, calculus isn't going to help me answer this question. And so then I look at it, and you can actually see it visibly by looking at the units between 2 and the beginning of my graph. So this point 80 logically is the closest point. So that would be the true answer. The problem is that the calculus portion failed because of the fact of the domain, and the question was outside of the domain. So let's do one that will actually match the problem I'm asking you to do.